Started, sir.
All right. So we continue with our discussion in CS772. Today I'll be doing probably the most important topic in deep learning for NLP, most fundamental topic, namely word embeddings. I call it more important than even transformer, because this showed a way of going from lexical discrete elements to the continuous representation of these lexical items, words, sentences, and so on, which really revolutionized the field. Because once you go into the continuous space, you can make use of lots of mathematical machinery there. And the motivation is also very nice. So cat and cot, they have a lot of alphabet similarity. C and T are common to both words. Whereas cat and dog, they don't have any alphabetical similarity. There is no common alphabet between them. Still, cat and dog are semantically more similar. Both are animals, carnivorous. Whereas cat and cot have no semantic similarity. Cat is an animal, cot is a piece of furniture. So how to capture this phenomenon, okay, where the words have no lexical similarity but huge semantic similarity, or vice versa, that is the main concern. And word embedding has huge application, word embedding to phrase embedding to sentence embedding, to paragraph embedding, to document embedding. You can think of any possibility where the continuous representation is involved. And without that, by the way, in converter, deconverter, transformer, these things will not be possible at all. Now, a one-slide recap in the last lecture. The weight change rule for single sigmoid cross entropy loss, they were given. And sorry, this was lecture 3, sorry. And we saw that the weight change rule with sigmoid and cross entropy is derivative free, independent of the derivative of the neuron that is being used, derivative of the output to input. Weight change for softmax layer, no hidden layer, and cross entropy loss was also done. Again, we saw that there is no derivative involved. So this raises a nice point about will vanishing gradient affect softmax, cross entropy based deep neural network, or sigmoid based neural network where cross entropy is used. So you read up on that, think about that. We will see that it depends on how sophisticated the deep learning system is and what we are using internally inside the deep neural network. Then we did the weight change rule for total sum square loss. TSS is also very important when we are dealing with multi-class classification problem. So if a particular document is both a legal document as well as economics document, then to classify the document into a particular class, 2 classes are involved. So since softmax is one take all, it cannot be used for multi-class classification. Then we discussed many fine points of backpropagation, local minimum, momentum factor, vanishing gradient, symmetry breaking, all of which are fine nuances which need to be understood in the context of the backpropagation algorithm. So we devoted considerable time and attention to backpropagation, which is worth it because this is the most important development in neural networks. Let's proceed. And we start with the linguistic foundation of word representation by vectors. I said that there is a linguistic phenomenon involved here because the semantic similarity of cat and dog is more than that of cat and cot. Even though there is phonetic sound similarity, there is spelling similarity, this is a phenomenon which needs to be captured. Does it have any use? It has a lot of use, because once we are in the semantic space and once we know the similarity and differences in the meaning of the words, then they are useful for any kind of NLP application. So we are discussing linguistic foundation of word representation by vectors. So this discussion is founded on a very fundamental linguistic contribution, namely Harris's distributional hypothesis. Words with similar distributional properties have similar meanings. This is due to the linguist Harris in 1970. In 1950s, Firth, another linguist, said, a word is known by the company it keeps. So the words in the context of another word determine its meaning or give a pointer to its meaning. Now this is in red. The word embeddings model differences in meaning rather than the absolute meaning itself. If you ask what is the meaning of dog, I'll say this vector represents the dog, but it is useful to measure the distance between the semantics of two words rather than the vector itself standing for the meaning of the word. That is because the components of the word vector are still not really interpretable. There has been work on interpretability, quite a few papers have come, but not much useful advancement to get the meanings of the components, without which, again, the meaning of the word vector itself or the word itself is not understood. So this is to model the difference. Now, the neural implementation to get the word embedding or to take the discrete word to a continuous space is through what is called the skip-gram network. The opposite of skip-gram is SIBO algorithm, continuous bag of word representation. In skip-gram, what happens is that we have an input layer, an intermediate layer, and an output layer. So this intermediate layer is a linear layer. There is no nonlinearity in it. Whereas the outermost layer is a softmax layer. How many such boxes does it have? It depends on how many words from the context we are prepared to take. So this particular case shows 2 words before and 2 words after. WT is the target word. And within each compartment, we have a number of neurons, which is equal to the vocabulary size of the language. For example, if WT is dog, then in the first compartment, I can have the words bark in the first compartment, which is for the word, let's say, bark. No, not the first. Let's take the word after dog. So that dog barks. So this particular compartment will represent bark, but not through what is called the one-hot representation, because all words in the vocabulary will appear And if the network is representing the word dog properly, then the neuron corresponding to the word bark will have the highest probability. So each compartment computes softmax. The next the next compartment is, let's say, the representation of the word loudly. The dog barks loudly. So here again, if everything is going all right, then loudly is the winner neuron. So you might find it a bit strange calling a neuron a word. That is how it is. There is one-to-one mapping between every neuron and the word, a word in the vocabulary. There is one-to-one mapping. And if the probability values are not computed properly, then maybe in the last compartment, instead of loudly, you have some other word, let's say water being the winner. So the dog barks water, which doesn't make any sense at all. So similarly, you have other neurons in these compartments, and their softmax computation is very important. So I hope you understand how the skipgram works. After training, if the training has gone well, then in skipgram, given that a word, it will produce the context words in the outermost layer, saying that my representation is fine. And where do we get the representation from? The representation itself will come from the weight vector, which goes from this compartment, the input compartment, to the intermediate layer. In the intermediate layer, you see, it will be one hot representation. One hot representation means only one neuron will be on. So in this case, dog is the word. So for dog, only one neuron is dedicated. All other neurons are 0. So if the vocabulary size is 100,000, then there are 99,999 neurons which are 0, and only one neuron is 1. Now it brings up the correct words here if the training is proper. And if the training is proper, then we look upon the word vector going from the weight vector going from dog to the intermediate layer as the representation of dog. Why is it so? Okay, we'll elaborate this, but you also think about it. The weight vector, which has dimension, let's say 300, because in the intermediate layer, there is huge dimensionality reduction. So typical size is something like 300 or 800 or 1000 neurons only. So there is severe compression of the representation. And the weight vector is also of size, let's say 1000. So this 1000 component weight vector represents the word dog. So similarly, if the training is fine, if we press cat, we might find words like mew and then milk, which are closely associated with the word cat in these compartments, okay, depending on the position of the word milk or mew. Again, if the representation is correct, these correct words will appear here if the weight vector is correct. And I can look upon that weight vector of cat as the representation of cat. Similarly, weight vector of dog coming from dog to the intermediate layer as the representation of dog. Now, why do I say that these are representing the words dog and cat? That's because these weights are such that they are activating the neurons properly and bringing the context words. And by Harris's distributional similarity, since the context words are correct, the representation of the word also must be correct. Not only that, the cosine similarity between cat and dog will be much higher Then the cosine similarity between cat and cot. Cosine similarity between what? Cosine similarity between the weight vector coming from cat neuron and the weight vector coming from dog neuron. Try to prove it yourself that these weight vectors will have high cosine similarity when I take cat and dog, but low cosine similarity when we take cat and cot. The hint answer is that there will be backpropagation from these words in the outermost layer. And the context words of cot are very, very different from that of context words of cat. And by backpropagation, the weight will be set such that these context words will be favored by these weights. And because of that, the cat and cot similarity will be low in terms of the weight vector going from the input to the intermediate layer. Okay, so this is what the skipgram is. And that is the most basic architecture which is used for skipgram, for word embedding. When is SIBO used? When is skipgram used? I leave it to you for your own reading. And there are situations where SIBO is better than skipgram, but skipgram is more popular. Do please read on skipgram and SIBO, and you should have a good understanding and insight into word embedding itself. Now, there is an illustration here. We have cat, lamp, and dog. So see the words in the vicinity of cat: mew, comfort, mice, furry, guttural, purr, carnivore, milk. See the words in the context of lamp: candle, light, flash, stand, shade, and halogen. There is no similarity of the context between cat and lamp. Okay, because we have taken a limited window. Still, there is hardly any common word, typically. But for cat and dog, we have here common words. Milk is common. And then vigilance, carnivore is common. Okay, and so on. So this is a typical. This is typically true. Words which are semantically similar have similar context words around them. So this is a remarkable observation coming from linguistics, and without that, the word embedding implementation would have been impossible without this theory. Now, what are the tests of representation? One of the important tests of representation is capturing similarity. Dog is more similar to cat than lamp because the input vector of dog and output vectors of associated words are more similar to output from the vector cat than from the vector lamp. Then we come to this understanding that since without Harris's distributional hypothesis, word embedding would have been impossible, we are saying that linguistics is the eye, computation is the body. It is distributional similarity which is providing the insight or the eye to move forward, and the skipgram architecture is giving the implementation, which is computation and is the body for getting word embedding. So the fine points in Harris's distributional hypothesis are the following. Words with similar distributional properties have similar meanings that we have already said. Harris mentions that the distributional approach models the difference in meaning rather than proper meaning itself. Okay, so that's a very important fundamental point. And going forward, we make use of that. Now we come to the nitty-gritties of the modeling itself. and to the maths involved. So what we want is to maximize the probability of Wt plus J given Wt and theta, the parameters of the architecture. Okay, so you see there are two product expressions. J is running over minus M2 plus M. That is, it is taking M words before the target words and M words after the target word. J not equal to 0 because J equal to 0 is the target word itself. And we do it for T equal to 1 to capital T, where capital T is the number of words. Okay, so 1 by T, product T1 to T, product pi M J going from minus M to M, probability of Wt plus J given Wt in the context of theta. This is the expression whose value we want to maximize. So it is intuitive, right? It is intuitive that we want to maximize the probability of the context words given the target word. So this maximization is equivalent to minimizing the negative of this expression. With negative of this expression because we are more used to gradient descent rather than gradient ascent, and backpropagation will do gradient descent. It can do a gradient ascent also, but that particular mathematical formulation is well worked out. Also, this negative expression looks more like a kind of entropy expression, which is useful. But we typically do not work with the expression itself. We work with log because log converts products to summation. So we minimize the loss L, which is minus of T equal to 1 to capital T, J equal to minus M to capital plus M, log PWT plus J given WT and theta. So this is our cardinal expression. This we would like to minimize. Minimize how? Minimize by gradient descent, more specifically by backpropagation. Okay. Now let us discuss this point of modeling the probability of context word given the input word and making it high. We want, say, probability of bark given dog. Then we'll take the weight vector from dog neuron to the projection layer, as we discussed in the skip-gram architecture. So this weight vector, we would like to give a notation. We call it U dog. So you see, going forward, the notation is going to be important. U is for input, V is for output. And the lower suffix dog indicates it is the weight vector for dog. Okay, and the weight vector is from the input compartment to the projection layer. So that is U dog. Take the weight vector to bark neuron from the projection layer. Now the destination is changed. The destination is the output layer compartment, output layer neuron. And the source is the projection layer. Unlike before, where the source was input and the destination was projection. Here, source is the projection and destination is the outermost layer. So when initialized, U dog and V bark give the initial estimates of the word vectors of dog and bark. So those are only initial estimates. Then by backpropagation and doing repeated correction on the context words in the output layer, we'll get the correct value of U dog and V bark. The weights and therefore the word vectors get fixed by backpropagation. So to model the probability, we need now an instrument. So this is how it is done. We take the dot product of U dog and V bark. You see both U dog and V bark are weight vectors. and their dot product is the cosine similarity between the two representations. We exponentiate the dot product, and they take softmax over all dot products over the whole vocabulary. So probability of bark given dog is given as e to the power ut dog u transpose dog dot v bark, okay, divided by e to the power ut dog vk, where vk runs over the whole vocabulary. So you can see it is it is really a softmax expression, and each of these dot products are actually scalars. Okay, and these scalars are going towards this probability calculation, which is a nice thing to do. So please stare at this formula for some time and convince yourself that this gives a probability. It gives a probability, no doubt, because of the way it is computed. But why this dot product of u and v, which is modeling the similarity, that is a nice thing to ponder over. So think of this exercise. Why cannot we model probability of bark given dog as the ratio of counts of bark, dog, and dog in the corpus, as we normally do by maximum likelihood estimate? Probability of bark given dog is find the number of times bark and dog appear together in some window, some context, whose length is fixed by u, and number of times dog appears in the corpus. And why this way of modeling probability, the dot product of weight vectors of input and output words through the dot product of input and output words, exponentiation and soft maxing. Why does it work? In particular, a more important question is why not ratio of counts? This is something you should ponder over. Now we work out a simple case of word to wake. Here is the example, very simple one. Suppose in our vocabulary we have 4 words: heavy, light, rain, and shower. Heavy is represented by this one hot representation, 0, 0, 0, 1. The word heavy is assigned the least significant position, not really significant, it is not a digit, the rightmost position. Light appears in the last but one position, in the second position, counted from right. Similarly, rain in the 3rd position, shower in the last position, position number 1. So these are one hot representations. So we want to predict as follows. When heavy comes in the input, the output should produce rain. When light comes in the input, output should produce shower. That is because the strength of association between heavy and rain is much more than between heavy and shower. Heavy and shower is not as frequent in the corpus as heavy rain. Similarly, light rain can come, light shower also can come. Maybe their counts are almost similar. But this is what we want. Okay, then what should we do? So look at this example, which is a simple one. And I don't think you will find this way of discussing word embedding in any of the papers or textbooks. This example I have created to make your understanding clear of word embedding. Now, any bigram is theoretically possible. For example, heavy, 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 light are possible, but unlikely to occur in the corpus. So language imposes constraints on what bigrams are possible. Domain and corpus also impose further restrictions. Okay. So we continue with the example. So our input output data is as follows: heavy U0, light U1, rain U2, shower U3. And output is also heavy V0, light V1, rain V2, and shower V3. Same representation, same position being occupied by the bit vector 1. Okay. So now what do we want? We want heavy to trigger the appearance of rain in the outermost layer. So U0, which is 0001, should bring 0100, which is rain in the outermost layer. Similarly, light should bring in shower. 0010 should produce 1000. Okay. Now here is the architecture. It is not drawn fully to make the network clear. It makes all the concepts clear without bringing in any cumbersome part of the architecture. So we understand that these input layer of neurons are fully connected to the projection layer. That means all the 4 neurons are connected to the first hidden layer and also to the second hidden layer. Similarly, the hidden layer neurons are fully connected to the 4 outermost layer neurons. So first hidden layer neuron is connected to 4 neurons in the outermost layer. Second hidden layer neuron also is connected to 4 outermost layer in the output layer. So since we have the representation for heavy, light, rain, and shower, we know what the architecture should produce. When I input 0001, thereby showing the architecture, the input word is heavy. The output we expect is something like this: 0.38 for rain, 0.6 for 0.38 for shower, 0.6 for rain, 0.01 for light, and 0.01 for heavy. So the probability of heavy when input is heavy is very small, because heavy does not appear as a bigram commonly. Similarly, heavy and light going together can happen. You can put 2 antonyms together in a context, but again low probability. But heavy rain has high probability of occurrence, that's why 0.6. And heavy shower also has some probability, therefore 0.38. So this is what should happen. Okay. So now let us see how this will happen. The projection layer, you see, has dimensionality reduction. 4 is the dimension of the input layer. Much longer or many more neurons in the outermost layer in practical networks. But the projection layer is reducing the dimensionality from 4 to 2. Okay. So this is the chain of thinking which I have already described to you. So the output from V2 should be the highest because of softmax. This way of converting an English statement into probability is quite insightful. Yes. Bigrams now have a probabilistic description. So we have to run a backpropagation, and we have to develop the word to weight change rule. Okay. We illustrate with only 4 words. So look at the conventions first. Conventions are very important. Otherwise, the derivation becomes messy and complex and ununderstandable. Capital U is used for the name of the neuron. So we have capital U0, capital U1, capital U2, capital U3. And the small letter is the output from the same neuron. Small u0, small u1, small u2, small u3. So u0 is the output when you have 0, 0, 0, 1, 1 at the bottommost neuron, representing the word heavy. Similarly, for the hidden layer neurons, capital H1 and capital H0 are the names of the neurons. The activation values are small h0 and small h1, which represent the output of the neurons. And on the outermost layer, we have capital V0, capital V1, capital V2, capital V3. These are the names of the neurons, and their outputs are V0, V1, V2, V3, all small letters, corresponding to the softmax values of the words heavy, light, rain, and shower. Weights always go from each neuron to all the neurons in the subsequent layer. Okay. So weights are indicated by small w. So index close to w is for the destination neuron. The other index is for the source neuron, as has been our convention during our discussion on the BP. Okay. So this is the network, as we have seen. Now more notation, and very useful and important notation. The net input to hidden and output layer neurons play an important role in the backpropagation, as we know. So net input to the hidden layer neurons are net H0 and net H1. Okay. So see that these are capital letters, and small net is the net input, which is a quantity. The net input to the outermost layer neurons are net V0, net V1, net V2, and net V3. Okay. So here it is. So these are the 4 neurons, and these are the 2 projection layer neurons. And before that, we have this input, projection, and output. The net input to every neuron is represented by net, and in the lower suffix, the name of that neuron. Okay. So now, what will be V0, V1, V2, and V3? Let us see. We are using softmax. So V0 is e to the power net V0. Okay, divided by e to the power net V0 plus e to the power net V1 plus e to the power net V2 plus e to the power net V3, as per the definition of softmax. Similarly, V1, similarly V2, similarly V3. Okay, the denominator remains the same. The numerator changes depending on the neuron we are concerned with. Now, one sec. Now, there is no nonlinearity in the hidden layer, because the hidden layer should do only dimensionality reduction. And it can be proved that in special cases, the hidden layer with linearity gives the principal components, and principal component of some interesting metrics in the neural network. Why dimensionality reduction? Dimensionality reduction achieves capturing the commonality of these distributional similarities across the worlds, which is a very important thing to do, because this dimensionality reduction captures the essential similarity between dog and cat. And the fact that cat and cot are not semantically similar are that is also captured by this dimensionality reduction. So net V1, net V0, net V3, etc. we would like to develop now. Remember that the projection layer is a linear layer. So net V0 will be nothing but WV0H0, the weight going from H0 to V0 as shown here, multiplied by H0 plus W V0 H1. Okay. And multiplied by the outputs coming from capital H0 and capital H1, namely small h0 and h1. And h0 we know is WH0 U0 plus WH0 U1 U1, WH0 U2 U2 plus WH0 U3 U3. Similarly, H1. Okay, so we'll continue after a very short break, and we'll develop this whole set of expressions, which you will see has a lot of nice regularity. Okay, we'll resume in a very brief while. Okay, so now we have got the expression for net V0, H0, H1, and then we see further simplifications are possible. So for heavy, only U0 is 1, U1, U2, U3 equal to 0. So H0 is W H0 U0 only. H1 is W H1 U0 only. So net V0 now becomes W V0 H0 into W H0 U0 plus W V0 H1 W H1 U0. Okay, how is it? Yeah, it is H0 and H1 values are plugged into the nets expression, and you get the product terms because product of these weight values are coming from these expressions. So you see net V0 is now coming out to be W V0 H0, W H0 U0 plus W V0 H1, W H1 U0. So what is it? It is nothing but the product of the row vector WH0 U0, WH1 U0, that is the weights emanating from U0 going to the projection layer, multiplied by WV0 H0, WV0 H1 by the column vector, which represents the weights going from the projection layer neuron to the neuron for the net, to the neuron for V0. Okay, whose net value we are concerned with to compute. So this is it. So this is a nice thing to remember, that the net value arriving at a neuron in the outermost layer is nothing but the dot product of the weight vector into the projection layer and the transpose of the weight vector going from the projection layer into the outermost layer neuron of interest. Okay. So the weight vector from U0 is called WU0, capital W. Weight vector into V0 is called WV0, W is capital. Slight liberty with notation, but has the intuitive advantage. So now we have been able to find out the net values, okay, which is of great importance. And it is in terms of the weight values only, which is also quite nice. Yeah. Now for heavy, the value of net V0 is dot product of WU0 and WV0 transpose. As you have already discussed, the weight vector going from the input layer neuron to the projection layer and the weight vector going from the projection layer into one particular output layer neuron. And it is depicted here pictorially also. So if this is the way we are developing the nets, then other net values also fall in place easily. If net V0 is composed out of the weight vector from U0 and weight vector into V0, then of course in this case the assumption is that the only one input layer neuron is on. So we are discussing everything for heavy, okay, only for the word heavy, where there is only one neuron in the input layer which is on. So net V1 we can then also very easily guess. It must be the dot product of WU0, the weight vector coming from the heavy neuron into the projection layer, multiplied by the projection layer's weights transpose going into V1, because it is net V1 we are considering. Similarly, net V2, similarly, net V3. So see how quite elegantly we have captured the net inputs arriving at the outermost neurons. Okay, and there is a systematicity to it. It all involves the weights going into the projection layer and coming out of the projection layer for the neurons which are of concern to us. So we want to maximize probability of rain V2 given heavy, which is U0. This probability is in terms of softmax. Probability of rain equal to V2. Probability of heavy equal to condition on probability of heavy equal to U0. Now V2 we know is e to the power net V2 divided by e to the power net V0 plus e to the power net V1 plus e to the power net V2 plus e to the power net V3 as per the requirement of softmax. So we would like to minimize the error function minus log of P rain given heavy. Now minus log of P rain given heavy is nothing but minus net V2 plus log of the denominator of the softmax expression. Because you see P rain given heavy, okay, P rain given heavy is nothing but V2, okay, and that is equal to the softmax expression, e to the power net V2 divided by this denominator. So this probability expression, conditional probability, is operated with log. Therefore, I have minus net V2 plus log of the denominator of the softmax expression. Net V2 is WU0, WV2 transpose, and then log of this denominator expression. Okay. So now we compute delta W V2 H0. This is what we are required to do in backpropagation. Again, gradient descent rule, and we have the machinery of backpropagation. Delta W V2 H0, the weight going from the projection layer neuron H0 to the output neuron V2 is minus eta delta E delta W V2 H0. Now E equal to minus net V2 plus log of the denominator of softmax. Now WU0 WV2 is WV2H0, small WV2H0, small WH0U0 plus small V2H1, small WH1U0. Okay, so this was derived before. So delta E delta W V2H0 is minus W80U0 plus this e to the power WV2 into WU0. Remember that this is how the softmax expression is constructed in our case. And then we have the denominator here multiplied by W80U0 because of the chain rule of derivative. Okay, so because of the chain rule of derivative, yes. So then we have minus W80U0 plus V2 into W80U0. So therefore, change in weight V2H0, that is the change in weight from projection layer neuron to the outermost layer neuron, is eta learning rate into 1 minus V2 into W80U0, which is eta into 1 minus V2 into OH0. So OH0 is nothing but the output from the hidden layer neuron. So W80U0 is, you can see, output from the hidden layer neuron H0. Okay, if you apply this input layer neurons values and the corresponding output at the projection layer, then this is what comes out. And 1 minus V2 comes from the taking out W80U0. Okay, minus W80U0, and this is the expression that we get. So this is very consistent with what we did for softmax and sigmoid. Okay, we have said that for cross entropy, we are indeed using cross entropy here. The change in weight is difference in target and observed value multiplied by the output coming from the source neuron. So target value is 1 always for the output layer neurons. And minus V2 is the observed value. So, and the loss function that we are using is actually cross entropy loss, okay, along with softmax. So as you have remarked before, softmax and cross entropy drops the derivative. This is what is happening anyway. So eta into 1 minus V2 OH0. So if V2 is close to 1, change in weight is also small. W80U0 is equal to the input H0 since U0 is 1, and to its output 2 since hidden neurons simply transmit out. Okay. So now we are going to discuss what happens to the weight change rule for other neurons when heavy is the input word. Let's say we are considering the weight change rule for rain. Okay. So we are interested in delta W V1H0. V10 is the other neuron. Okay, sorry. Other neuron is the slight neuron. So V1H0. And here, delta W V1H0 is minus eta delta E delta W V1H0. Again, we have minus net V2 when we take the log and log of the denominator. So net V2 is WU0 WV2 T, as we have already designed, and the log of the denominator. So WU0 WV2 is coming out to be equal to small WV2H0 small W H0U0 plus small W V2H1 into small W H1U0. Okay, so all these maths you should be able to work out. They are following very logically from one step to the next. And this flow is very logical. But I insist that you work it out properly. Now delta E, delta W, V180 will produce for the first expression W, V280, W80U0 as 0 because this product does not depend on small w V180 plus e to the power w V1 WU0 divided by the denominator as is required by the softmax expression. So by chain rule again, where this when I take this summation expression, only the term that will survive the partial derivative operation is small w H0U0. Okay, so this particular way it will survive the partial derivative, and then this will give rise to V1 W80U0. So change in weight V1H0 for the input word heavy is minus eta V1 W80U0, which is equal to eta into 0 minus V1 output of H0, which is intuitively correct. Because when heavy is input, the output of slight neuron should be 0. Okay, and you have observed some value V1. So 0 minus V1 is the target minus observed. So as per our derivation before, the softmax and the entropy combination is giving me change in weight equal to learning rate into difference in target and observed multiplied by the output of the source neuron. This is also consistent and intuitive. So it is the same weight change rule for any neuron in the output layer, which is a beauty. We have learning rate into difference into output of the source neuron. Difference of what? Difference of the target value and the observed value. Okay. So now we interpret the weight change rule for V1. If we assume W80U0 to be positive, then for training U0 to V2, that is heavy to rain, if V2 is not 1, then delta W V2H0 is positive. So it will boost the output there. For the same input, delta W V1H0, that is the weight going to the light neuron, is negative. So that weight will get depressed. Okay, so the net effect of this is that the heavy neuron will boost the weight value of rain and will depress the weight value of light, which should not appear with heavy. So the two weight changes are of opposite sign. The effect is that while V2 increases, V1 decreases for the input U0 as it should be, since we want to increase probability of finding rain, probability of rain winning given the input heavy, and depress all other probabilities. Now, what about the weight change for input to hidden layer? Say W80U0, the heavy neuron to the first projection layer neuron. Again, gradient descent applies. Delta W80U0 is minus eta. Eta is learning rate. Delta E, delta W80U0. And E is net V2 plus log of this denominator. E is same for whether you're considering hidden layer or not. E is E, which is measured at the outermost layer. So net V2 is minus WU0 WV2T and log of the denominator. Now we have seen before WU0 W transpose V2 is small w V2H0, small w H0U0 plus small w v2 h1, small w h1 u0. So now delta E, delta W H0 U0. So we're taking the derivative of the error function with respect to a hidden weight, okay, not the outermost layer neuron's weight. And this we know happens by backpropagation, but let us look at it from a more fundamental perspective. So, so when we take the derivative, we have minus W V2H0 plus W V0H0 e to the power W V0 WU0 W V1H0 and this W V2H0 and e to the power expression and so on, and also the denominator. The product expressions of W's are coming because of the chain rule of derivative. And when we open this out, we get minus W V2H0. The V0 is coming because of e to the power W V0 into W U0 divided by the denominator, which by definition is V0 in the softmax layer. Similarly, W V1 H0 V1, W V2 H0 V2, W V3 H0 V3. So these are products of outputs of outermost layer neurons and the weight values going from the projection layer into the outermost layer. So see that the expression here is longer and little more cumbersome. Now delta W H0 U0 is coming out to be a learning rate into 1 minus V2 W V2 H0, okay, minus W V0 H0 V0 minus W V1 H0 V1 minus W V3 H0 V3. This is coming because V0 plus V1 plus V2 V3 is 1. Okay, this one is coming from the summation of those probabilities. And the minuses are coming from minuses are coming from the negative expression there. So this is equal to eta into 1 minus V2 W V2 H0 plus 0 minus V0 W V0 H0 plus 0 minus V1 W V1 H0 plus 0 minus V3 W V3 H0 multiplied by 1. And a nice thing has happened here. We are getting the change in weight to be equal to the backpropagated deltas coming from the outermost layer. The backpropagated deltas, the deltas in the outermost layer are simply the difference between target and the observed, multiplied by the weights used in reverse. Okay, you see, so this is very nice. So we have 1 minus V2 as the backpropagated delta multiplied by W V2 H0, the weight in reverse. 0 minus V0 backpropagated, 0 minus V1, 0 minus V3, all these are backpropagated. And I can multiply the whole expression by 1. So this multiplied by is as if multiplied by U0. U0 we know is 1. All other neuron values are 0. So it is squarely fitting into the discussion on backpropagation and backpropagated delta. So this means we could have also arrived at this expression simply from the universal derivation that we did in the backpropagation class. Okay, derivation of the universal rule for backpropagation for hidden layer output, hidden layer weight fixation, and for outermost layer weight fixation. So all this is fitting into one single picture, which is very nice. So then weight change rule for the hidden layer neurons are coming out to be the same expression, learning rate into backpropagated delta. into input from source neuron. Notice that the derivative of the station, that is the neuron's derivative, will not picture because the neurons are linear neurons. And the derivative of output to input there is on 1, simply 1. Okay, so that is not coming. Also, it would not have come because of the use of softmax and entropy, cross entropy, mainly in the outermost layer. In the hidden layer, we are not using softmax or cross entropy. But because the derivative is 1, station derivative is 1, it is not coming in the expression. Okay, so we'll end the class with some fundamental discussion on a very important concept, namely representation learning. So the basic questions which are asked are, what is a good representation? At what granularity should the representation be? Should we represent words or n-grams or phrases or sentences or all of them? Sentence is important. I bank with SBI. I took a stroll on the river bank. This bank sanctions loans quickly. So each bank should have a different representation depending on the context. But we know that if we take simply word embedding from the corpora, then that will not happen. So we are interested in context-specific representation also. And we have to learn these representations from the data. Now we have already seen how simple the word embedding algorithm is. It is called self-supervision, because for every word, we want words in the context to appear in the outermost layer. No special data requirement. Simply you have sentences and the context window you fix, and you take a large amount of corpus. The probability values are fixed properly, and through backpropagation also they get very nice, accurate values. Now, principle behind the representation is the proverb. A man is known by the company he keeps. Similarly, a word is known or represented by the company it keeps. Company in this case means distributional similarity. The starting point of all this representation is the one-hot representation. We arrange the words in a lexicographic order. We define a vector V of size L, where L is the lexicon. And for a word WI in the ith position, set the ith bit to 1. All other bits are 0. So cosine similarity of any pair is 0. That would give a wrong picture. Okay, so if you use one-hot representation, then the dot product is always coming out to be 0. So one-hot representation may be the correct starting point, but this is not the final representation. Otherwise, it gives 0 for any pair of words, independent of its semantic similarity. Now we ask for the representation we should learn or not learn. One-hot representation does not capture many nuances, for example, semantic similarity, but it's a good starting point. Co-occurrence also does not fully capture all the facets, but it's a good starting point again. Let's explain co-occurrence. Co-occurrence means the words, it is a word-by-word matrix, where for a row which is for a particular word, the column words are either ticked or non-ticked, saying that they appear in the context of the word. So that is called a co-occurrence matrix. So co-occurrence matrix also, when given 1, 0, each row is represented by a 1, 0 vector. And we can put the count of the times the word appears in the context. Then we'll have an integer vector. But that representation also is not fully satisfactory. You have to learn the representation from the data, because that representation only is language specific. It is not data specific. So the learning objective is to maximize the context probability. Now we come to embeddings. The first foundational point is that it's a way of taking a discrete entity to a continuous space. So 1, 2, 3, 2.7, 2 by 9, 22 by half, that is square root of 22, are numerical symbols. They are points on the real line, and they give rise to natural embedding. The symbol 2 has a natural embedding on the real line. Words embeddings are not so intuitive, right? How to get them? So the purpose of embedding is to enter the geometric space and take advantage of the distance measures, Euclidean distance, Riemannian distance, and so on. Distance gives a way of computing the similarity. Cross entropy, for example, is a way of computing the similarity. Foundational point 3 is that similarity and difference. Recognizing similarity and difference is the foundation of intelligence. Intelligent beings see the difference between entities, and many times very specialized knowledge is required to see the difference. Let's say between a healthy plant and a plant that has been infected by insects. Okay, there may not be any outside manifestation, apparent outside gross manifestation, but very fine manifestation there is there. So a plant doctor with sophisticated knowledge will be able to see that difference. A lot of pattern recognition is devoted to this task of similarity and difference detection. And a lot of NLP is actually based on text similarity. Words, phrases, sentence, paras, and so on. Lexical, syntactic, semantic, pragmatic, these are horizontals. And words, phrases, etc. are verticals on which similarity is computed. So similarity study we have done in machine translation, for example, we have found that Hindi is more similar to Bangla, more similar to Marathi than Bangla. Hindi is more similar to Bangla and Marathi than English. Manipuri is not similar to any of these other 4 languages. So it is an important study. Isometricity is also important for representation. So we want to represent multilinguality and multilingual entities in single space. So for example, dog, kutta, bag, tiger, kitab, book, they should be all together, independent of the language. So cross-lingual mapping is done. There are adversarial learning paradigms by which cross-lingual mappings are done, and words with similar meaning across languages are put together. This is foundation number 4, syntagmatic and paradigmatic relations. So in syntagmatic relation, we look at the contextual similarity. In paradigmatic, we look at the property similarity. So cat is an animal, dog is an animal, therefore they're similar, more similar than cat and lamb. So this is called paradigmatic similarity. It is because of the animal property that these 2 words are together. In IIT Bombay, we have created an all Indian language wordnets with the help of other institutes, and these capture primarily paradigmatic relation. ConceptNet is another very famous knowledge graph like WordNet, but it primarily captures syntagmatic relations. This shows the picture of a WordNet subgraph. House and home are synonymous words. Their parts are backyard, veranda, study. House and home belong to a larger class called dwelling and abode. and so on. So deep learning and knowledge graph integration is a very important topic, has been always important in spite of large language models and so on, because we are interested in using small language models also. So that becomes possible only when we use deep learning along with a lot of knowledge. So lexical and semantic relations appear in the word net in the form of synonymy, hypernymy, antonymy, meronymy, etc. So there is a different discussion which we can do later. Paradigmatic relations are for substitutability. The cat is drinking milk. The animal is drinking milk. Here, cat and animal are substitutable. And that shows that they have similar properties, at least same similar part of speech. Foundation 5 is learning and learning objective. The probability of getting the context word given the target should be maximized. This is the skip-gram objective. Probability of getting the target given the context word should be maximized. That is the CBO objective. So these are the learning objectives which we work with. So that finishes some fundamental discussion on representation learning. And let me finish here today. Today's discussion was totally devoted to word embedding, a very, very important topic in deep learning. Thank you.